In this video, we're going to look at why the counting digits trick works for multiplying decimals. So let's look at this problem, 4 and 8 tenths times 3 and 71 hundredths. And if I were to multiply this out using traditional multiplication, I would write the number with the most digits on the top, and then I would go ahead and do my regular traditional multiplication algorithm. Let's see, this will be 24 and 5, which is 29. Go on to the next place value, 4 times 1, 4 times 7, and that would be 14. That was an 8. And then I would add everything up. And when I'm done, then I'm going to go back and I'm going to count the number of digits behind the decimal in the problem, in this case 3, and I'm going to bump back 1, 2, 3 digits in my answer. So my answer becomes 17 and 808 thousandths. Let's now dig a little bit deeper and see if we can figure out what's going on here. So we could rewrite our original problem as 4 and 8 tenths times 3 and 71 hundredths. And then we could change it to an improper fraction, so we could write 48 tenths times 371 over 100. And of course, the commutative property of multiplication says I can multiply this in whatever order I want. I can put 48 tenths first, or I can put 371 hundredths first. It doesn't really matter. But I'm going to go ahead and leave it the way I have it. So what I'm going to do now is I would have to multiply 48 times 371. And then for the denominator, I would do 10 times 100. That's fairly simple, so that's 1,000. 48 times 371 is actually what I just did over here. I did 371 times 48 because I completely ignored the decimal points as I did this multiplication problem. So I actually already know the answer to that. The answer to that is 17,808. And then my denominator is still 1,000. Now, if we remember that fractions really are just division problems, this problem right here, this fraction right here, becomes 17,808 divided by 1,000. And if we could just quickly think about place value, let's say we have a 4-digit number, and our 4-digit number is, let's call it 5,000. Its decimal point would be after the whole number, because decimal points, all they do is separate whole numbers from parts of numbers. If we were to divide this number by 10, 5,000 divided by 10, I can do that in my head. I know 5,000 divided by 10 is 500. Its decimal point still divides the whole numbers from the parts. If I were to divide the original number 5,000 by 100, I would get to 50. Decimal point still comes after it. If I were to divide my original number 5,000 by 1,000, I would get to 5. And again, decimal point right after the whole numbers. Notice that each time that I divide by a power of 10, my number, my entire number right here, really just shifts over one place value, because I can actually fill all this in. Now you can see the 5,000, it's just shifted over one place value to the right. I could do the same thing right here. We can see the 5,000, 5 with 3 zeros. It's shifted over 2 place values to the right. And then when I divided by 1,000 here at the end, it shifted over 3 place values to the right. So every time I divide by a power of 10, we can say that digits shift one place value to the right. So now going back to my problem right over here, I know that I'm going to need to take 17,808 and I need to divide it by 1,000. Well, I know when I divide by a power of 10, I shift digits one place value to the right. So the decimal point comes right after 17,808 because it separates whole numbers from parts. But I'm dividing by not one power of 10, I'm dividing by 3 powers of 10, which is 1,000. So I need to shift my digits 3 place values to the right. So 1, 2, 3. That means these 3 digits right here are going to go over to the right, and I will be left with 17, then the decimal point, and then my 3 ones that move to the right, so 17 and 808 thousandths. Now what we're doing when we count the number of digits behind decimal points in a problem is we're really just counting the number of powers of 10 that we're eventually going to have to divide by. So we had a 1 right here, And then we had 2 right here that made the 100. So altogether we had 3 powers of 10 we need to divide by. And when we bumped back the decimal point, that's really just an optical illusion. It's actually our digits shifting to the right, because decimal points don't actually move. But you can think of this when we're shifting the digits to the right, the decimal appears to shift to the left.